Hello, in this lecture I will talk about mathematical induction. Mathematical induction is a logical method to prove that a statement, a claim or an equation is true for all the natural numbers. A natural number is a positive integer like 1, 2, 3, 4, etc. There are two stages in mathematical induction. In the first stage, you will check that the statement is true for n that equals to 1. And only then you will move to the second stage. And in the second stage, actually we will create two equations. That is to say, we will assume that the statement is true for n, and then we will prove that the statement must be true also for n plus 1. Okay, so the first equation will be for n. It will be the induction's hypothesis or induction's assumption that the statement is true for n. And then we will create the expression for n plus 1, and we will prove it when we rely on our assumption that the statement is true for n. Okay, and actually I will repeat again. In the first stage, we check if the statement is true for n that equals to 1, and only when we passed the test and it is indeed true for n that equals to 1, only then we will proceed to the second stage. And in the second stage, we will assume that the statement is true for n, and we will rely on this assumption in order to prove that the statement is also true for n plus 1. Now I will explain what is the logic behind the mathematical induction. In the first stage, we actually proved that the statement is true for n that equals to 1. And in the second stage, we proved that if the statement is true for n, then it must be true for n plus 1. So, after we actually proved or checked that the statement is true for n that equals to 1, we can say that because of the fact that we proved that if the statement is true for n, then it must be true for n plus 1, so we can say that because of the fact that we know that the statement is true for 1, then it must be true also for 1 plus 1, according to our general proof, that if it is true for n, it must be also true for n plus 1. So we know that it is true for n that equals to 1, because we checked that it is true for n that equals to 1. So we can deduce that it also must be true for 1 plus 1, that is 2, according to our general proof. So now we know that the statement is true for n that equals to 2. So we will repeat on the same process in order to prove that the statement also true for n that equals to 3. So we will say that because we know that the statement is true for n that equals to 2, it must be true for n that equals 2 plus 1, according to our general proof that if it is true for n, it must be true for n plus 1. Now we know that it is true for n that equals to 2, so it must be true for n plus 1, that is to say for 2 plus 1. So it is true for n that equals to 3. And again, we will repeat on the same process in order to prove that n is also, that the statement is also, that the statement is also true for 4. Yes? Because we know that the statement is true for 3, and according to our general proof that if it is true for n, it must be true for n plus 1. So now that we know that it is true for n that equals to 3, so it also must be true for 3 plus 1. So that is the reason that it's also true for n that equals to 4. So in this way we actually prove that the statement is true for all the natural numbers. So that is the reason behind the mathematical induction. Okay, so now in order to clarify the topic, I will give you 2 examples. We will start with the first example. So 1 plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. So this is the example. 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So we have to prove that this statement is true for all the natural numbers. Okay? So we will start with the first stage. That is to say, we will check if the statement is true for n that equals to 1. Okay. So in this side of the equation we will have 1, because n equals to 1. Here it is n times n plus 1 divided by 2, so n is 1. So it is 1 times 1 plus 1 all divided by 2 equals to 1 plus 1 is 2, and 2 times 1 is 1. Two divided by 2 is 1. 1 equals to 1. So we passed the first test, the first stage, because we indeed proved that this statement is true for n that equals to 1. So now we can move to the second stage. That is to say, we will assume that the statement is true for n, and relying on that assumption, we will prove it for n plus 1. Okay, so the first equation will be our inductions hypothesis. Okay. Or inductions assumptions. That the statement is true for n. Okay, so the expression for n will be 1 plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. So this is the inductions hypothesis. We assume that the statement is true for n. So we assume that this equation is true, and relying on our assumption, we will prove the original statement, this statement is true for n plus 1. Okay, so we will create the statement for n plus 1, and then we will prove that the statement is true. So the expression for n plus 1 will be 1 plus 2 plus 3 plus n plus 1, because we have to prove that the statement is true for n plus 1. Okay, so we will add the numbers until we will arrive to n plus 1. and then in the other side of the equation we have n times n plus 1 divided by 2. So right here we have to prove that we have to prove that the second expression for n plus 1 is true. Okay, on the other side of the expression that we have to prove, we have to prove it for n plus 1. So wherever it is written in the original statement n, we will write n plus 1 because we want to prove that the statement is true for n plus 1. So here is written n, we will write n plus 1, and here is also written n, so we will also write n plus 1, and it is n plus 1, so we will add to n plus 1 1, all divided by 2. Okay, so the second equation is for n plus 1, and we have to prove that this equation is actually true. This expression for n plus 1 is true, and the expression for n plus 1 is 1 plus 2 plus 3 plus n plus 1 equals, here in the other side of the equation, wherever is written n in the original equation, we will write n plus 1 because we have to prove that the statement is true for n plus 1. So we actually substituted n by n plus 1. We substituted n from the original statement by n plus 1. Okay, here is written n, so we wrote n plus 1, and here is also written n, so we wrote n plus 1. Okay, here it is n plus 1 times n plus 1 plus 1, so n plus 1 plus 1 is n plus 2, so we will write it down. So here it is the same expression like here, but we n plus 1 plus 1 is n plus 2, so we wrote here n plus 2. That is the only change from here to here. Okay, so actually if we look on this expression in the green color, we know, according to our assumption, or according to the induction's assumption, that this expression equals to n times n plus 1 divided by 2. Okay, first of all, you also should notice that these two expressions are exactly the same expressions, and this expression equals to n times n plus 1 divided by 2. This is according to our induction's hypothesis or induction's assumption. So we actually can substitute this expression by n times n plus 1 divided by 2, because they equal to each other. So that's what we will do now. So we write it down. So instead of 1 plus 2 plus 3 plus n, plus n, we can write, as I've already told you, those two expressions identical. So according to our assumption, it is equal to n times n plus 1 divided by 2. So we will write n times n plus 1 divided by 2 plus, here it is written on n plus 1, so we will copy it as it is, all equals to n plus 1 times n plus 2 divided by 2. We will copy it as it is. So the only change that we did in the second equation that we must to prove that it is true, the only change is we substitute this expression by n times n plus 1 divided by 2, because according to the induction hypothesis, these two expressions are equal to each other, and this expression is identical to this. So we can substitute this expression by n times n plus 1 divided by 2. Okay, so we must prove that the second equation is true. Here in this equation we have n plus 1 in both sides of the equation, so we will divide the equation by n plus 1. Okay. And after we divide the equation by n plus 1, we will get that n times n plus 1 divided by n plus 1 is n divided by 2, plus n plus 1 divided by n plus 1 is 1, and n plus 1 times n plus 2 divided by n plus 1 is n plus 2, n divided by 2. So I will explain again. N times n plus 1 divided by n plus 1 is n divided by 2, n plus 1 divided by n plus 1 is 1, and n plus 1 times n plus 2 divided by n plus 1 is n plus 2, and it is divided by 2. So we can separate this expression to two parts. Okay, because we have n plus 2 divided by 2, we can create here two expressions. It will be n divided by 2 plus 2 divided by 2. Okay. So after we divide this expression to two expressions, we got here n divided by 2 plus 2 divided by 2 equals to n divided by 2 plus 1. We didn't touch this expression, we copy it as it is, and here we divided this expression to two parts. Okay, and 2 divided by 2 equals to 1. So we will get that n divided by 2 plus 1 equals to n divided by 2 plus 1. So we got an identity, n divided by 2 plus 1 equals to n divided by 2 plus 1. So we actually proved that the second expression for n plus 1 is true, or in other words, we proved that if we assume that that our statement is true for n, then it must be true also for n plus 1. And in this way, actually, we proved that this original statement is true for all the n's, all the natural numbers. Why? I will explain why. Because in the first stage, we proved that this statement is true for n that equals to 1. Okay, we proved that this statement is true for n that equals to 1. And in the second stage, we proved that if it is true for n, it also must be true for n plus 1. So, in this way, we actually proved that this statement is true for all the natural numbers, and I will explain why. Because we have already proved that it is true for n, and according to our general proof that if it is true for n, it also must be true for n plus 1, we can say that now that we know that it is true for n that equals to 1, so it also must be true for 2, that is 1 plus 1. Because according to our general proof, if it is true for n, it also must be true for n plus 1, and n equals to 1, so it must also be true for 1 plus 1, that is 2. And then we can again do the same process in order to prove that it's also true for n that equals to 3, because now we know that it is true for n that equals to 2, and according to our general proof, it also must be true for n plus 1. If it is true for n, it also must be true for n plus 1. So now that n equals to 2, it also must be true for 2 plus 1, that is 3. Then after we know that it is true for 3, we will, in the same process, prove that it is also true for 4, because according to our general proof that if it is true for n, it also must be true for n plus 1. And now that we know that the n equals to 3, and it is true for n equals to 3, so it must also be true for n plus 1, that is to say for 3 plus 1, that is 4. And for that reason, it is also true for 4. And in the same way, we will prove that it is true for 5, 6, 7, etc. And so in this way, we proved that this statement is true for all the natural numbers. Okay, so I will give you the second example. 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square, all divided by 2. So we have to prove that this statement is true for all the natural numbers. We will start with the first stage. That is to say, we will check if the statement is true for n that equals to 1. Okay, so in this side of the equation we will have 1 to the power of 3 equals n equals to 1, so it is only 1 to the power of 3 equals to n squared times n plus 1 half square divided by 2, and n equals to 1, so it is 1 square times 1 plus 1 square, all divided by 2, equals to 1 square is 1, 1 plus 1 is 2, so it is 2 square divided by 2, equals to 1 times 1, 2 square is 4. I made a mistake. The original statement is n to the power of 3 to 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n square times n plus 1 square, all divided by 4. So we divide it by 4 and not by 2. So here we will correct it. Okay, so 1 times 4 is 4, and 4 divided by 4 is 1, and 1 to the power of 3 is 1, equals to 1. So we passed the test, and we actually verified that this statement is true for n that equals to 1. So it is indeed true for n that equals to 1. Now we will move to the second stage. That is to say, we will assume that the statement is true for n, and then we will prove it for n plus 1. So the first equation will be the induction's assumption. Or induction's hypothesis. So the statement for n is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3. So equals to n squared times n plus 1 square, all divided by 4. Okay, we divide it by 4. So this is actually the induction's hypothesis or induction's assumption. We assume that the statement is true for n. Okay, and as we rely, now we will rely on this assumption in order to prove that the statement is true for n plus 1. So we will create the expression for n plus 1, and we will prove that it is true relying on our assumption for n. Relying on our assumption that it is true for n. So the expression for n plus 1 will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus. So the expression is for n plus 1. So we will start with 1. Yes, we will start to add the numbers for 1, and we will not stop on n square to the power of 3 because the expression is for n plus 1. So we will also add n plus 1 to the power of 3 because the expression is for n plus 1. Okay, so it is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3. All equals. Now here in the original statement we have n squared times n plus 1 squared divided by 4. So wherever we have n, we will substitute it by n plus 1 because the expression in the second equation is for n plus 1. Okay, so we substitute n by n plus 1. Okay, so the expression in the other side of the equation for n plus 1 will be, instead of n, we will write n plus 1. So it will be n plus 1 square times n plus 1. So it is n plus 1 in the original statement, and we are writing the statement for n plus 1. So it will be n plus 1 plus 1. All divided by 4. Okay, so here, as you can see, it is n plus 1 plus 1. That is, of course, n plus 2. So we will write it down. N to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3 equals to n plus 1 square times n plus 2 square, all divided by 4. So the only change from this line to this line is that we changed n plus 1 to n plus 2. The other things are the same. We copy it from here to here, and actually we will do the same process as we did in the first example. We should watch on this expression, and actually this expression is exactly the same expression as this expression. They are identical. 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3. So they are identical, and according to our assumption, or according to induction's assumption or induction's hypothesis, this expression equals to n squared times n plus 1 squared divided by 4. And this expression equals to this. So we can substitute this expression by n squared times n plus 1 squared all divided by 4. Why we can substitute it? Because they are equal to each other according to our assumption, according to induction's hypothesis. So we will do it now. So instead of this expression, we will write n squared times n plus 1 squared all divided by 4. Okay, these two expressions are equal to each other. Okay, these expressions are equal to each other. And the rest we will copy it as it is. So, as you can see, this line is almost identical to this line. The only thing that we changed is that we substitute this expression by n squared times n plus 1 squared divided by 4, because according to the induction's hypothesis, they are equal to each other. Okay, so now if you look on this line, you can see that we have in both sides of the equation n plus 1 squared, so we can divide the equation by n plus 1 squared. Okay. Okay. N squared times n plus 1 squared divided by n plus 1 squared will be n squared, and n squared is divided by 4 plus n plus 1 to the power of 3 divided by n plus 1 squared will be n plus 1, and n plus 1 squared times n plus 2 squared divided by n plus 1 squared will be n plus 2 squared. So here we got this line after we divided both sides of the equation by n plus 1 squared, because n squared times n plus 1 squared divided by n plus 1 is n plus 1 squared is n squared, and divided by 4, and n plus 1 to the power of 3 divided by n plus 1 squared will be n plus 1, and n plus 1 squared times n plus 2 squared divided by n plus 1 squared will be n plus 2 squared, is divided by 4. So now we can multiply both sides of the equation by 4. Okay. So after we divided both sides of the equation, we got by 4, we got that actually n squared divided by 4 times 4 is n squared, and n plus 1 multiplied by 4 is 4n plus 1, and n plus 2 squared divided by 4 multiplied by 4 will be n plus 2 squared. So here we actually can open the brackets n plus 2 square is n plus 2 times n plus 2. So here, after we open the brackets, we got n squared plus 4 times n is 4n, 4 times 1 is 4, and n plus 2 square is n plus 2 times n plus 2. So we will open the brackets again. N times n is n squared, plus n times 2 is 2n, 2 times n is 2n, plus 4, 2 times 2 is 4. So we get so we got the identity, then square plus 4n plus 4 equals to n squared plus 4n plus 4. Here I actually opened the brackets, it's very simple. N times n is n squared, 2 times n is 2n, and again 2 times n is 2n, 2 times 2 is 4, and here we will get that n squared plus 2n plus 2n is 4n, plus 4 equals to n squared plus 4n plus 4. So we actually proved that the second expression for n plus 1 is true, or we proved in general that if the original statement is true for n, then it must be true for n plus 1. And in this way, we actually proved that our original statement is true for all the natural numbers. Okay, because in the first stage we proved that it is true for n that equals to 1, and then we proved in general that if it is true for n, it must be also true for n plus 1. Okay, so we can say that because of the fact that we know that it is true for n that equals to 1, and we proved in general that if it is true for n, it must be also true for n plus 1. So we know that it is true for n that equals to 1, and according to our general proof, it must be also true for 1 plus 1. N plus 1 is 1 plus 1 because n equals to 1. So in this way we proved that is actually also true for 2. And then we will repeat on the same process in order to prove that is true for 3, because we know now that it is true for n that equals to 2, and according to our general proof that if it is true for n, it also must be true for n plus 1. We can say now that we know that it is true for n that equals to 2, and according to our general proof, it also must be true for n plus 1, that is to say for 2 plus 1, that is 3, and then we can, in the same process, can prove that it is also true for n that equals to 4, to 5, to 6, and so on. Okay, so in this way we actually proved that the statement is true for all the natural numbers. Okay, so we will summarize the lecture and say that mathematical induction is a logical method to prove that a statement, an equation is true for all the natural numbers, and a natural number is a positive integer. And we have two stages in mathematical induction. In the first stage, we will prove, we will check if the statement is true for n that equals to 1, and then in the second, and only if we passed this test, and indeed it is true for n that equals to 1, then we will proceed to the second stage. That is to say, we will assume that the statement is true for n, and then we will prove it for n plus 1. And actually in this way we proved that the statement is true for all the natural numbers. Why? Because we, in the first stage, we proved it for n that equals to 1. And then in the second stage we proved that if it is true for n, it also must be true for n plus 1. So because of the fact that we know that it's true for n that equals to 1, we can deduce from our general proof that if it is true for n, it must be also true for n plus 1. We can deduce that if it is true for n that equals to 1, it also must be true for n that equals to 1 plus 1, that is 2. And we can do the same process in order to prove that is also true for n that equals to 3, 4, 5, 6, 7, etc. So in this way we actually proved in the mathematical induction that the statement is true for all the natural numbers. Okay, thank you very much.